Well, I am Miguel Saavedra Chimal, and I am going to talk about the design of estimators based on a reticular scheme. I'm doing my practices in the profession at the Instituto Nacional de Astrofísica, Óptica y Electrónica, INAOE. I have three main parts: introduction, development, and conclusion. And we are going to start with the introduction. Well, the description of this project has three main parts: the literature review, the mathematical analysis, and the development of a method for computing the Fourier coefficients. And this method is going to be based in a reticular scheme of derivatives. And well, this method should take a long time, so it is not expected to have a complete method. What are our objectives? Well, to understand the harmonic estimation method through the reticular scheme of this derivative calculation of the sinusoidal signal. How? By making a careful analysis of the existing methods. And why? To determine harmonics with a small number of samples. Our measurement will be through possible simulation on MATLAB to demonstrate the advances found. Well, our main goal is to do a full report with an understandable explanation of the estimators that are going to be used, and a description of the clear advances of a method capable of this harmonic behavior with a small number of samples. That is very important. Well, how are we going to do this? First of all, we have to review bibliographic other methods already used. Then we have to develop these numerical derivatives. Then to find a solution of these equation systems, to do tests. And then, well, after all, we have to analyze the results, and probably with this MATLAB simulation. Well, what specification do we have? In the state of art, we already have, because of INAOE, that if we take a stimulus signal like a sinus omega t, well, we can find the second derivative, and then dividing the second derivative over the stimulus signal, and we're going to obtain something like this, like the omega frequency, by doing just operations over just the data that we had before. Well, now if we now calculate this new equation, this one here, well, we can, after few methods, few mathematics, we find that we can also obtain the amplitude. We can obtain the amplitude by doing the square root of the original signal multiplied by the original signal minus the original signal squared over the second derivative. Well, you can see here that we don't have to use any amplitude or frequency or any other values, just data, and just with the data we can obtain these results and these Fourier coefficients like the amplitude. Well, why are we talking about Fourier coefficients? Well, we can define something like this, like a original signal. This represents the principal component, and these both represent the distortion, the harmonic distortion. So if we get this main idea of the linearity of the amplitude, we can obtain the second derivative. And after that, we can have a second function like v2, and this is the sum of the first one plus the second one plus the second derivative of the original signal. After doing this, we have something like this, like show here, and we can observe that a very important thing is that we don't have anymore the frequency omega, so we can proceed with only the Fourier coefficients, and we don't have this principal component. So this is very useful for us. After that, we can do the same thing for a V3, and this time we have to do 4 times the V2 and adding this to the second derivative of this second equation. After having that, we can have a series of equations, and this is what we are going to call our reticular scheme. So reticular means this series of equations, and with these equations that I've checked or all reassembled from different papers, well, we can obtain an VK plus 1, so to any number of harmonics desired. So we have here a sum of this first distortion with a coefficient of an and the number of harmonics to until n, and the same thing with bn because we have here a cosinus. So we have to repeat this thing until there is no harmonic component. And how do we know where we have already reached this point? Well, we have to take into consider the fundamental calculus. So we're going to apply the derivatives, but just with the expressions. So we all know that we need well, when h is too small, near to 0, we can already use this formula here and use the original signal minus this original signal, shift the h positions, and then divided that to h that is very close to 0. And if we do this thing, but for the second derivative, we can observe that after substituting these formulas here above that I've already put together, we find this one. Here we can see that we can obtain the second derivative from just things or data of the original signal, just shifted h positions or 2 times h positions. So if we express this like from v, we have this that I have already said, these h positions shifted here to the left and here to the right, and this h to the square. So we already have this second derivative after just few data, and with this second derivative we can return to this analysis of linearity and to do just this formula of amplitude to determine this showed at the beginning, this one here. We can make the square root of the main signal multiplied by the main signal minus the main signal square divided to the second derivative. Okay, so after doing everything, we already can show the results and graph these results by making some force and making this iteratively, repeatedly. So what I've learned, I acquired many new knowledge because this subject was totally unknown for me. But now I have a clear idea of the estimation of Fourier coefficients through these reticular schemes or series of equations based on these derivatives. And well, I've also learned different methods for estimating these Fourier coefficients, and the use of derivatives through this fundamental calculation, right? In this calculation and graphing of the derivatives, it isn't so easy as I have thought, but now I can do that. And well, I've also learned the importance of these coefficients estimates for power electric and power quality. Well, the conclusion is that this application is a little bit limited because we need just continuous signals, and for continuous signals we need derivatives. So this is a theme, but it is very useful for certain applications like the power factor measurements, and it generates an efficient method that needs few samples. That is very important because we can already calculate the amplitude and frequency just at the beginning of the signal. Just having the first 3 data, we can already have this. Thank you, and this was my presentation.